Hopefully. So, we will prove with you Radon-Nikodym theorem by means of the following lemma. In this lemma, we will construct a function, measurable function, that satisfies these conditions. These conditions, of course, provided that for any rational number q, there is this measurable set such that this difference is 0, measure of the difference is 0 for any two rational points, and we suppose that this sigma algebra for any measure space. For any measure space. Now, we will prove this lemma in two steps. Indeed, we will do the same for Radon-Nikodym theorem. Firstly, we will suppose good enough situation. This good enough situation is that these sets BR, suppose that this is increasing family. If this is increasing family of measurable sets, then, of course, this trivially will be 0. Then we will define function f of x by definition as the infimum of R such that f of x belongs to B of R. So x belongs to B of R. Please look at the picture. So we have some increasing family of sets. Now this is some x. This is some x. I don't say that x eventually will belong to some set. If not, then this infimum is infinity.
It is rho or R.
Q less or equal than R. R, I mean the same R as here. Okay. Now, if this x eventually belongs to some Bs, then we will take the infimum value of this s. It will be the value of the function. Okay? Okay, so this function is well defined. This function is well defined. Then, if you have that all Br will be x outside of them, then we have that function is infinity, is infimum for empty family. Now look, this is the function. Then what is easy to see? It's easy to see that function satisfies this condition. Yeah? Then if why this condition? If x belongs to Br, then definitely f of x less or equal than R, because it is infimum. It is infimum for some family that belongs to this family, clearly less or equal. That? If x does not belong to Br, then we have that f of x more or equal than R. Why? If not, it's also easy to see. If not, then we will have that it means that f of x is strictly smaller than R. It is strictly smaller than some R minus epsilon. Okay? And then we will have that x belongs to some Br minus epsilon, but family is increasing. Family is increasing. We will have that x belongs to Br, so this is a contradiction. So definitely this function satisfies these two conditions. Okay? If once more, if x does not belong to all this union of all this Br, it means that function will take infinite value, and it, of course, will have this condition. Now look, of course, we need to check that function is measurable, so we don't have this by free. Yeah? What does it mean, measurable? Function is measurable means that for any alpha, rational, irrational, the set, we have that the set x such that f of x is smaller than alpha is measurable. We need that the set is measurable. But of course, since this alpha can be approximated, for example, from below by rational values. So this is the union of x such that f less or equal than Rn. Yeah? And this is Rn increases to alpha. We have this representation. And then these sets are measurable, since this sets are Br. Okay? So we will have that this is measurable set. So function is measurable. Indeed, that's almost all. Only we need to check that other function. Other function must be the same. Here, the same. If we have G has the same property, it means that G is less or equal than R for Br, etc., etc. Then what do we have? We have the following embeddings. We have that R such that we have that R such that Gx is smaller than R, x smaller than R. This is inside of R such that x belongs to BR, inside of R such that G of x less or equal than R. It just follows from this property. So please, if you write then G on BR less or equal than R and here G on the complete more or equal, then you will see this. Otherwise, again, you will have contradictions. It's just this discussion only for function G. And then what do we have from here? We have that set Q is dense on the line, Therefore, what is G of x? What is G of x? G of x, it is just infimum for that set. Okay? We consider all R which are larger than Gx. So this is concrete value Gx. This is infimum for this set. Infimum for this set R such that G strictly less than R. At the same time, it is infimum for R such that G less or equal than R. Of course, we can take infimum for these closed sets, you see. But by this sandwich property, since our set, this set of R is between them, yeah, so we have that is the same as infimum of x such that x infimum of R such that x belongs to BR, but this is just fx. It's just fx by definition of the function. So since function G has the same property, we have these two embeddings, so we can we have two sets, overset, subset, and superset for this set which defines the function f. If you take infimum for both of them, we will have just clearly the value G of x, and then since it is infimum of that one, it is f of x. So now they're not only almost the same, almost everywhere the same, but they're exactly the same in this case. Okay? Please your questions about the first part. This is the proof of the case when the family is monotonically increasing. Now for any BR, we can take Z, which is union of BQ minus BR for LQ less than R. For LQ less than R. This is now what do we have? We have family. We have countable family of sets with this property. Yeah. And now we take the union of that type. Since the union countable, then we have that this measure of Z clearly is 0. Yeah. And what else? And we have that AR and AR, maybe BR prime. BR prime, which is BR union of Z, is increasing. It's easy to check. Now, this is increasing, yeah? This is increasing. Check it. And then we will apply the first part of the proof for this U family, and we will construct the function f for this family. But the function f for this family, of course, is almost everywhere as function for this family. The difference only on this set Z measure is 0, yeah? Then 1 implies that there exists f such that, etc. For the first part, look, once more. For first part, we have not almost everywhere, we have everywhere. We have everywhere, smaller than R, everywhere larger than R. But now we will have almost everywhere because of this set Z, such that f is more or equal almost everywhere than R on the complement on x minus BR prime, etc. So please your questions. This is lemma. This is lemma. We will prove now Radon-Nikodym theorem by means of this lemma. What is Radon-Nikodym theorem? Maybe questions about lemma? Huh? Radon-Nikodym theorem. This is theorem 4. Theorem 4, important Radon-Nikodym theorem. Why this theorem is important? Because of important in mathematics, of course. It shows the structure of measures. If one measure is absolutely continuous with respect to another, then it is just integral, nothing more. And also it has some applications. Some applications in the theory of probability. Since the theory of probability by Radon-Nikodym theorem, it's possible to show existence of so-called conditional expectations. These conditional expectations is just a kind of absolutely continuous, some restrictions of measure, probability measure. Also, you can look the internet or you can find other sources There are some applications, financial mathematics, etc., everywhere in the economy where they use theory of probability to give some mathematical description of process. So there are applications. What is this Radon-Nikodym theorem? It's the following. We have x, m, and mu. It's supposed that this is sigma finite. This is important. Sigma finite is, as we'll see with you, sigma finite measures space. Measures space. So, once more, what does it mean? It means that x, it is union of xn, and mu of xn is finite, nothing more. Union of some measurable sets. Now, suppose that this is sigma finite measure space. Now, I want to give you two versions of this Radon-Nikodym theorem. Firstly, more general version that we will prove with you. We will have that mu is absolutely continuous with respect to mu. Now look, I rewrite definition of this absolute continuity. Now mu is absolutely continuous with respect to mu, so it is just definition. Okay, and this is just typical example of absolutely continuous measure. And that's all in general setting. In general setting, then there exists function f, and in general setting, this function can take infinite value. Please look at this detail. If we will, the next version, if we will ask this also sigma finite is many books. In many books, they requires, in internet, for example, Wikipedia, in Bogachev and other books, they consider it finite case or sigma finite case. Then that will be finite function. But we will prove this for Lemma for any absolutely continuous measure. That is, if measure mu is sigma finite, and this measure is absolutely continuous with respect to mu, it does not follow in general. This measure is sigma finite, as I will show you now in simple example. So there exists function in extended sense, of course measurable, again in this extended sense, infinity is excluded, such that we have that nu of e equals integral f d mu for any measurable set mu. Of course, it's supposed that these two measures have the same domain. They have the same domain, this sigma algebra. So this is statement of Radon-Nikodym theorem. Since this function is not unique, but it's unique almost everywhere, for other function, other g, with nu of e equal integral g d mu for any e, it follows that these two functions are the same. They are the same mu almost everywhere. But mu almost everywhere, of course, will imply nu almost everywhere, yeah? Since they are the same except the set of zero measure mu. But if it is zero measure mu, this is also nu almost everywhere, yeah? The measure mu, in principle, it follows one from another. Okay, so this is statement, more general statement of Radon-Nikodym theorem. Once more, the idea is that it's not just example. It's not only example of absolutely continuous measure, but this is typical example in the sense that any absolutely continuous can be written in this way for some function f that we will construct with you now. Or, this is another version. Another version on the same condition. If we have that nu is sigma finite, then, I mean, the first line is the same. And of course, it is absolutely continuous. Then we will have that there exists f from x into r plus. There is usual finite function measurable, such that with the same condition, nu equals. Okay. So, if you will ask in addition that function measuring nu is sigma finite, then the function will be constructed, will be finite, usual function, proper function. In general, it can take infinite value. Now, before the proof, we will use this lemma. So I will try to save the statement of the lemma. Before the proof, I hope we will do this in 20 minutes, of Radon-Nikodym theorem, some remark and some definition. At the beginning, definition. Definition is the following. So, this function f, which exists by Radon-Nikodym theorem, is called so-called Radon-Nikodym derivative. This is the measure of nu with respect to mu. And this is called Radon-Nikodym derivative. Radon-Nikodym derivative. Of course, derivative of measure mu with respect to measure mu. So this function, in principle, may be infinity. Why this is the derivative? It follows from the substitution. This is calculus. What do we have? We have by this representation. Now we will integrate. Let us integrate with respect to measure nu. If we integrate with respect to measure nu, that is what is function. What is the integral g d nu over this any set E, over this any integral, or maybe the whole space X. Then what is this? From there we will have that this is g multiplied by f, and here d mu. Yeah, since this is just this corresponding value. Therefore, it is the same as in calculus. The same as in calculus. If you use the substitution, so we will. It is just derivative. It is derivative of that one with respect to that one. Okay, this is explanation. So by this substitution of these integrals. Now remark. I want to repeat that. If we have mu is sigma finite, and nu is absolutely continuous, it does not follow that nu is sigma finite. And what is more, in principle, mu may be finite. It's just take trivial measure. Just take trivial measure, and we will see with you. So, for example, we can take any sigma finite measure, and we can take nu of empty set is 0, and nu is infinity for any e which is not empty set. This is a measure. This is a function, sigma additive, etc. Of course, it's trivial, but nevertheless, sigma additivity follows trivially, so we have all conditions. And now, of course, this trivial measure will be absolutely continuous with respect to any measure mu. Yeah, because if it is not any. Yeah. No, I'm sorry. Not for any measure mu. Let's take measure mu in the following way. For example, we can take, such that the measure mu has 0 value only on empty set. It's easy to construct this measure. For example, we can take x equals n, mu equals subset of n, and we can take mu of E, something as the sum. For example, 2 minus k. K belongs to E. Yeah. So please, this is a measure. It's not counting. It's something integration with respect to natural integration with respect to this weight. Now, what do we have? We have that mu E is 0 if and only if E is empty set. Yeah, of course. If not empty, then it will have some value, since we consider only natural numbers now. Okay. Now, therefore, of course, from here it follows that nu of E is 0. So this is not only sigma finite. This is finite measure. This is absolutely continuous measure with respect to mu, but not, of course, not sigma finite. No, not sigma finite, of course. You see? Questions? So it's not the case. Now, but nevertheless, this satisfies the first version of Radon-Nikodym theorem. Yeah? Because in first version, it's not. We don't say that the second measure is sigma finite. Then, if we want to have this representation, then definitely we have to take here a function identical equal infinity. This is good measurable function, and then we will have this representation. We have this representation f d mu. Why? Because if it is empty set, then this is 0. Yes. If it's not empty set, then this is infinity. Okay, no, we have representation. Okay. Now, but before the proof of Radon-Nikodym theorem, let's consider one example. You have to feel this. What is this derivative? Let's consider typical. By the way, it's very easy to write problems for this subject. Just take any measure of that type, etc. So let's take the same x and mu as above. Yeah. And let's take nu of E, not this trivial measure, but something, any summation for natural. For example, we can take counting measure. What is counting measure? It is 1. If you take summation for all k inside of E. So this is just counting measure, yeah? So this is the number of natural, since E is only natural, yeah, by this definition. So it is number of points, or maybe infinity, if its set is infinite. So this is counting measure. This is counting measure, counting of natural number measure. And now look, of course this is also, of course this measure is absolutely continuous with respect to mu, yeah, because any measure is absolutely continuous with respect to this measure. Since this takes 0 value only for empty set, trivially, yeah? Any measure is absolutely continuous with respect to that one. And the inverse, by the way, of course, it's not difficult to see that since this is also any measure is absolutely continuous with respect to this mu, since it takes 0 value only for empty set, okay? Now, therefore, by Radon-Nikodym theorem, but now they are sigma finite, both, clearly, yeah? They are both sigma finite, because n it is the union of sets 1, etc. n, okay? Now, we have this definitely sigma finite. Therefore, by Radon-Nikodym theorem, there are corresponding functions, and we have to find these derivatives. What are these derivatives? We will have, so what do we want to have? How to find it? Look, we want to have that nu of E, indeed, maybe it's better to write immediately, or maybe in this way, nu of E, it is just the sum of elements, the number of elements in the set E. It is the integral, but what is the integral with respect to mu? Integral, it is this summation, nothing more, yeah? So it is some value of the function. It is the value of the function at k, and here 2 minus k, and k belongs to the E. But we want to have this one, yeah? We want to have this one for any this term, of the term. So definitely we have that derivative d nu with respect to d mu, this Radon-Nikodym derivative, it is 2k for natural. It is function which is defined only on natural numbers, and it has this value, 2k, yeah? And if you substitute, we will have here just 1. And it's not difficult to see that the same as in calculus, if we have derivative of inverse function, that is, if we now, since if both one measure is absolutely continuous with respect to another at inverse, then we will have that d, mu with respect to this d nu. Now it will be 2 minus k, again by the trivial this representation. So please your questions about this example. We see now how to find this Radon-Nikodym derivative. It's enough to write this identity and consider different values of E, different values of E. For example, if it's given on some countable set, just consider singletons, and you will have the value of the function in the singleton, okay? Since we understand what's the value of singleton, what the measure of mu measure singleton and new measure of the singleton. If it's not singleton, then consider some intervals, etc. Okay, now let's start to prove Radon-Nikodym theorem, but again, I track you. Please ask questions. Okay, now look, Radon-Nikodym theorem. We will use this Hand decomposition. Of course, Hand decomposition for signed measure, but we will construct some special signed measure. So this is the proof, of course, not of this, but of Radon-Nikodym theorem. Also, we will present the proof in 2 parts. In the first part, we will suppose that mu is finite. Mu is finite measure, suppose, at first. And then we will extend it for sigma finite case. Now, we will consider with you this version, but by the way, we will see what we will have if this measure also is sigma finite. Then we will see that function will be finite. But in general, it can take, as we will see from the first remark, it can take infinite value. What is more, it can be identical infinity. So suppose that measure mu is finite. What we will do? We will take, we will fix any rational number, q, and consider and we will consider with you signed measure. Of course, this mu, once more, this mu and nu, they are usual measures now, usual measures. They can take only positive value. But we will consider with you this difference. We will consider with you this difference, R nu minus R mu. Now this is signed measure, okay? And since this is finite, we have that this measure is well defined. The case infinity minus infinity is excluded, okay? So this is well defined. Now, by the Hahn theorem, by the Hahn decomposition theorem, by theorem 2, we have that there are two sets. We have that X, it is union of two sets, AR, union with BR. AR, it is positive with respect to that one. BR is negative. That is, we have that nu, okay, we have that AR is positive with respect to nu minus R mu, and BR is negative, okay? It's negative, so we have this. Now, we will consider different values of R. What we have to see with you immediately? We see with you immediately that if R increases, then we have that BR increases. Do you see this or not? Of course, because if we have, and by the way, AR decreases. Because if we have that R, what does it mean that it is on BR subset? It means that nu less or equal than R mu. But if it is less or equal than R mu, of course it's less or equal than R plus epsilon mu, okay? So if we will take something, then we will enlarge the set. We will enlarge the set. That is, means that BR is inside of BR plus epsilon. Yeah? Do you see this? Yeah? If we enlarge R, we will enlarge the set. We enlarge the set. Since for the whole BR, we will have this inequality. Therefore, this BR is completely inside BR plus epsilon. So it is larger. Now, it's easy to see. Now, therefore, we can draw the following picture. We have here BQ. Q is smaller than R, by the way. Now, it will be something larger. It is BR. And now, what is A? Here we have AQ. This is AQ, yeah? Since this is the complement. And here it is AR. It is AR. So AR decreases. AR decreases. Now, we will, that's not all. Oh, that's all. It's enough now. Now we will construct, or maybe, let's look, what is AR? Of course, we can do this for any rational, But it's interesting to consider only positive rational. Since if you take R equals 0 or R equals negative, then we'll have trivial decomposition. Since now it will be just usual measure if R is negative, yeah? It will be usual measure, and for usual measure decomposition is very trivial. That is A0, it is X, and B0 we can take empty set. Of course we can take some null set, but without loss of generality we can move this null set to A0. Is it clear or not? Because if we take 0, it is just measure nu. Nu is usual measure. Usual measure. Usual measure is positive everywhere. And all subsets are positive, okay? Therefore it is A0. And for negative, of course, it's here. So it's the interesting situation if R is positive. Now, so this is some remark. That we have this stuff. That we will use it now. Now, we will introduce with you CQR. We will introduce with you CQR as BQ minus BR. Please look at the lemma. Please look at this lemma 3. We will have with you, for any rational, indeed for any positive rational, we will consider with you the sets with 0 measure mu. So it is just this difference. What does it mean that this difference? This is BQ intersected to AR, since AR is complement to BR. Yeah, this is just the same. Yeah. Now, why? Of course, this is measurable stuff. What should we see with you? Then we have to see with you that measure of CQR is 0. Why this measure is 0? Of course, it follows from this picture immediately. Because AR, it is something which is outside of BR, and BQ is something which is inside of BR. So they have empty intersection, okay? From this picture. Of course, picture is not the proof, so maybe it's better to write the following. So if we have, what do we have? we have that nu minus r mu for this set C, QR. What is this? This is inside of AR. Inside of AR. If it's inside of AR, this is more or equal than 0. Yes? But it is not inside of AR. So for Q it is negative. Therefore, what do we have from here? We have here R mu of CQR less or equal that nu of CQR. But on other hand, since this is inside of BQR, in the same way we can write less or equal than Q and mu of CQR. Since the same we can write, but only less or equal than 0 if we put Q instead of R. Yeah, since it's inside of Q. But Q is smaller than R. When is it possible? When is it possible? It is possible only if this is 0, since Q is strictly smaller than R. But this is illustration. This is illustration. So up to 0 set, they are disjoint. They are disjoint, the sets. The sets are disjoint, okay? Now please your questions about this first step. Introductory step to define the sets. Now, I will move here. Now we will define the function f, yeah? But we will define the function f not for b, but for a. Of course, it's not so important. Now, since we have this condition, we can apply lemma 3. Then by lemma 3, we have that there exists measurable function such that we have that the value of the function on this AR will be more or equal than R. It is AR. It is AR. More or equal than almost everywhere. And the value of function of BR less or equal than R, again, almost everywhere. This is just by this condition, by the definition of C. Yeah? It is just this difference. Please your questions, interrupt me. We have time to discuss if you will not see something. Now, so function exists and function measurable. What is more? What is more? In our case, we don't say here in lemma 3, but in our case, we have that function is non-negative. Why? Here, r equals 0 implies that the value of the function on a0, but what is a0? As we just saw with you, a0 it is x, yeah? It is more or equal than r. More or equal than r, it is 0. Therefore, we have that function almost everywhere is non-negative, non-negative. So, just as in Radon-Nikodym Theorem, we have now with you some function, and we want to prove that this function satisfies this condition. Okay? So we have some non-negative function. Now, the next step is the following. The next step, fix any measurable set E, but it's finite case, so measure of E is finite, of course, it's subset of X, and any n, let be natural, any n, and we will consider with you EK. And this EK will be defined as intersection of E of BK plus 1 over n and minus B of K over n. So since this family increases, yeah, the sets will give increasing family. So this is K over n, and this is K plus 1 over n. So K plus 1 over n, and here there is some set E, yeah? So it is just the part inside of this kind of annulus, okay? It is some part, of course it's measurable set, and of course again we have, if we will do this, it is the same as to write that is inside of AR, AKN. Now, we have, but K is not from minus n to n, K from 0 to infinity. K from 0 to infinity, so it's interesting to consider only positive values, we understand with you. Now, that's not all. Let E infinity, by definition, will be E minus this union, K from 0 to infinity of EK. All stuff is measurable, all are disjoint. We have disjoint decomposition. Since we have E, it is E infinity union with this EK from 0 to infinity. This is disjoint decomposition of E into some countable union of measurable sets. Okay? And now, what we will do? We will carefully compare the value of measures on this concrete set EK. Now, if no questions, I will do this at the beginning. Since this is disjoint decomposition, then we can write that nu of E, it is nu of E infinity plus the sum of nu of EK from 0 to infinity, since this is disjoint and this nu is a measure. And now the main part of the proof. The main part of the proof is the following. What do we have? We have that EK, it is subset of this set. It is subset of B, K plus 1 over N intersected to A, Kn. It's better now to write in this way, since A it is just the it is just the complement to this BKN. And then from here we have that the function is defined in this way. The function is defined in this way. Therefore, we can compare immediately, estimate from both parts integral of this function over function f over the set ek. That is, it is integral over set ek of function f d mu. What do we understand about function f? So this function is moral equal, and here we have k over n, since it belongs to ak, and function moral equal than this value, and the measure of ek, of course, because it is just bound to a function from above, by this value, from below. It is bound to function f from below by this value, and the measure of this set, yes? I feel that you don't follow the proof, so I'm ready to stop and repeat some stuff. What do we do? We fix at the beginning for any rational number, for any positive rational, it's interesting to consider positive, no negative, we have this signed measure, well defined. For this signed measure, we have Hahn decomposition. This Hahn decomposition, as we will see with you, has some monotonicity property. If we will enlarge parameter, then we will enlarge B and we will decrease A. From here it follows, then this set, which will be crucial for us in what follows, has zero measure if Q is smaller than R. So we are in the position of the first lemma. But we will do this now. That is for any R. For any R, there is some function. Okay? But we will consider this for any special R. We will consider for any special rational values. N is natural, and we will consider values of the type k over n. But k not from minus n to n, k for any value from 0 to infinity. For negative, it's not interesting. If you take 0 or negative, then we will have trivial value, then a0 immediately to x, okay? Therefore, we have this, we will consider this decomposition. We decompose set E into union of sets EK, which belongs to this annually. And then there is some complement. The part where function will take infinite value here, yeah? Because what is clearly for us? That the value of infinity, it is infinity, of course. Yeah? Now it's not problem. Now, and now we want to prove this crucial, we have a function non-negative, measurable, only we need to prove this stuff. We need to prove this representation. We will do this by decomposition, by this decomposition of the set into small parts. Now, we consider this ek inside of this intersection. Since it is inside of ak over n, then function is larger than k over n. We have trivially that stuff. Since it is smaller than k plus 1 n, then we will have this inequality. Okay? Okay. Now, that's not all. Okay, I want to say this. Now I will erase it here. We will continue, but we will continue with measure nu. Again, we will estimate now the value, new value of the set ek. Again, ek is inside of B. I will write this again. K plus 1 over n. So what does it mean? It means that nu minus k plus 1 over n of this set, indeed for any subset, particularly for this, but we will take for this ek. So this is negative. This is negative. This is negative with respect to this signed measure. Okay? A is positive. This is negative. If it is negative, it means that this is less or equal than 0 for any subset. For any subset. Particularly for this ek. So this is negative. Okay? Therefore, what does it mean? It means that nu of ek less or equal than k plus, I don't write here mu. I don't write here mu. Of course, we have to write it. Q plus 1 over n, and here mu of ek. So here it's written. Now, on the other hand, it's clear, yeah? On the other hand, ek belongs to ak over n, because ek it is just intersection, inside of the intersection. Therefore, the same measure, but with new parameter, we have that nu minus k over n mu. Now, for this EKS for any subset is positive, not negative. Therefore, we have that nu of ek more or equal than k over n mu of ek. It's very good for inequalities, since we estimate this from below and from above, but very closed stuff. Very closed stuff. Okay? Do you see this? Now, what do we have from here? From here we have that nu of ek. Again, let's look at that one. It will be no. Let's start from mu of ek. What do I want to? I want to take integral. Okay. Let's compare these two inequalities. Okay. So what do we have from first one? From first one we have nu of ek minus 1 over n mu of ek. Yeah. It is less or equal from the first one. It is k over n of that stuff. Yeah. But k over n of that stuff can be estimated from above by this integral. Therefore, this is less or equal than integral ek f d mu. Yeah? Okay? Is it clear? Just we consider together this inequality and this inequality and this inequality. Yeah? That's not all. Since this integral less or equal than k plus 1 over n mu of ek, it is what written below. But now this will be less or equal than mu of ek, and here plus 1 over n and mu of ek. So please your questions. We have this for any k, so now we are ready to take summation. If we will take summation, we will have just the measure. And then we will have, this is for k. Also what we will have? For finite k. Also we have that nu of E infinity equals integral over f d mu over E infinity. Also for infinity we have exactly, not less or equal, but exactly. Why? Since this is 0 equals 0, this is 0 and this is 0, if mu of E infinity is 0. If this is 0, that integral is 0, yes? By definition of integral. But since measure is absolutely continuous, that this is also 0. Or this is infinity equals infinity if mu of E infinity is positive. If this is positive, then this is infinity, since we understand with u that function, it seems to me I wrote here this somewhere, I don't remember where, that function on E infinity is infinity by this definition, okay? Therefore, we have formally, not formally, actually, we have this form also. And now we will take the sum for all k from 0 to infinity plus this infinity value. And this is, by the way, is the difference, I will finish soon. It is, by the way, it is the difference between the first and the second case. If this measure is sigma finite, then we will have the finite function, since now there is no this set E infinity. but it's measured in general, there is no restriction, then in principle we can include this one. And from here, after summation, what do we have? If we take the whole sum, we will have that nu of E, I take the sum for all k, and include this infinity. Minus 1 over n, and here mu of E. Of course, we look, we have this not only for nu, of course we have this for the same for mu. It is disjoint decomposition, so the same we have for mu. And if you take all summation, it will be for mu, less or equal. Now all these integrals are over disjoint sets, so it will be integral f d mu, and this will be less or equal the nu of E plus 1 over n, and here mu E, indeed that's all for the first case. Why that's all for the first case? And the second case will say that it follows easily. Since now, what do we have? This is just what we need. Why? Because we have, since measure of E is finite, supposition, first supposition, measure is finite, and nu n is any number. N is any number, here there is no n, here there is no n. Move n to infinity, we'll have that they are the same. Please your questions. This is Radon-Nikodym theorem, the main part. Indeed, it's better to finish this now. I mean, so this is the case when measure is finite, and this is the proof. It would be great if we will ask something. But if measure is not finite, if measure is sigma finite, then we can reduce to this situation. Then what do we have? We have that x, it is union of xn, and without loss of generality, we can take xn disjoint. And now what do we have? And then we will have that for any xn, for any n, there exists function fn. Of course, this function fn lives only on xn. Yeah? Support of the function on this xn. And then we can take function f as the union of fn. Nobody says that it's convergent series. Of course, it's convergent in the sense that it's well defined, so they have different support. The functions have different support, but we will consider x1, x2, etc., etc. Here take one function, here take another function, and take this. And then we will have desired by sigma additivity, and then we will have that, since we have, what do we have? We have that new, okay, we can take ek, em. What is em? It is union of xn, n from 1 to m, okay? And then we will have that nu of em equals integral over em of f, of this function f. Indeed, not f, but you can take restriction d mu. And this is for any m, and this is for any m. So by additivity, we have all we need. Then we will have for the whole set E. Okay. Unfortunately, we don't have time to consider examples. I will do this next time with you, if you will come, of course, on Monday. I recommend you to come, since I'm going to give. These problems are very standard, but this is important technique to find Lebesgue decomposition of the measure, or find the Radon-Nikodym derivative, etc., etc. We'll do this next time. Now we have 2 minutes. It's better if you will ask questions, or I will repeat again the main idea of the proof. The main idea of the proof is to decompose set E, as a union of sets which are which have very good condition in the sense that the measure is very close. Yeah. Measure is very close in the sense that on this set EK, the measure nu here is almost the same as we need, up to some small term. But this term, as we will see with you, neglectable, at least for this finite case. And then we will take the sum and have the result. Okay, this is important, one of the most important theorem in analysis, especially in the theory of measure and integral. So you have to understand at least the idea of this theorem. Next time we will start from the example. Again, this is a rather standard example that shows that this measure maybe is not sigma finite, yeah? But if this measure is not sigma finite, we don't have this result. We don't have this result. Of course, you can find this example in any textbook, but I'm going to consider in class. So this condition is very important. Sigma finite is of mu. Okay, that's all. Please discuss with your friends the date and time and place of the second midterm. It's time to write it. See you. Bye.